This is Math 270, Chapter 1, Section 1.1 Notes. So we're dealing with limits, a numerical and graphical approach. Before I begin with the lecture, well, before I begin with the notes, I should say, I want to give you a little background on limits. The limiting process, as I mentioned in the beginning of the course, is the whole, it's what makes up calculus. Everything in calculus involves the limiting process. So in this course we ask you to understand it a little bit and be able to evaluate limits, but we certainly do not go in depth as we would in a 173, a regular calculus course. So we hope that you understand it a little bit, and you do have to show that you can evaluate some limits. Alright, so number 1 says, as x approaches a, the limit of f of x is L, written the limit as x approaches a of f of x equals L. So we got some new notation here. If all values of f of x are close to L for values of x that are sufficiently close but not equal to a, the limit L must be a unique real number. So all this is saying is, as we're getting closer to a value on the x-axis, we want to evaluate what value we're getting close to on the y-axis, looking at a function. So you see we have a picture here, and we're looking at the limit as x approaches 2. This is how we would say that in mathematical notation of this y function. So y is equal to x squared minus x plus 2. And we have a picture here. So looking at the picture, we want to look at, we have a parabola here. And as we go, let me change colors, go along this parabola and we get close to 2, and on the left side, and we can do it again on the right, we want to look at what value is over here on the y-axis, and of course it's 4. So that's what a limit is. You can see it's not that interesting for a problem like this, because it's a pretty basic function basically, but we use these basic functions to have you understand limits first, and then we get into areas where the limit is a little more complicated. Okay, so that's it for that page, page 2. Alright, so here are some examples where the limit starts to get a little bit more interesting. The first part A, well, you'll see that it says that the limit equals L for all of these graphs. And you'll also notice that all the graphs look almost the same, but there's going to be slight difference in each one. Alright, the first one, nice smooth graph, no holes in it. And as we get close to A, so I'm looking at going to A on both sides, I approach L. And we don't know what L is. It could be 4, it could be 5, it could be 100, it could be 1,000. It's just some number, and the same with A. When we look at example B, we see that there's a hole there. But it doesn't matter with limits, because we're not asking what the function equals at A, we're asking what the limit is as we get close to A. So you'll notice we're doing the same thing here. I'm getting closer and closer to A along the graph, and then I want to look over and see what my y value is as I get close. And again, it's L. Even though the actual value of the function is down here, something less than L. And then example C is very similar to B, except the function doesn't exist at A at all. If I asked you what f of A was here, you would say does not exist. But if I asked you for the limit as x approaches a of f of x, you would say it is L. So the function doesn't have to exist for the limit to exist. Okay, number 3, complete each of the statements. As x approaches -4, the value of 3x plus 7 approaches what value? Well, 3x plus 7 is just a line if we were to graph it. So if you want to know what y value it approaches, you can just plug it in. Alright, so we would have 3 times -4 plus 7. Yeah. And that would equal -12 plus 7 is -5. So if there's nothing interesting going on, then it's pretty straightforward. The limit is just going to be whatever the function value is. And part B says the notation, the limit, well, I won't read it out, is red. Well, so of course we're going to start with the limit. Let's see if I can zoom in here. And then the arrow is as x approaches four, and then the plus sign means from the right. And then of g of x. So that's how we would read all that out. Alright, number 4 is a theorem. As x approaches a, the limit of f of x is L if the limit from the left exists and the limit from the right exists, and both limits are L. So what that's saying is the limit only exists if it's the same, if it exists and it's the same in both directions, which is all we've seen so far. So they give you an example. They show that from the left, so let me get that little pointy thing here. I got an arrow pointing here. It says the limit as x approaches a, that's from the left. That's what that means. We just saw from the right, now we're seeing from the left. And then, so the limit as x approaches a from the left is equal to L. And then on the other side, we see that the limit as x approaches a from the right is also L. So it's okay to conclude that that limit does exist since they're both the same. And yeah, so in other words, the right and left-hand limits have to be equal in order for the limit to exist. So what we want is where they don't both, where they're not both the same. So we have a graph here, and it says to use the graph to answer the following. So A says the limit as x approaches 2 from the left. So we would be using this graph here, following it along from the left, and approaching 2, look back over, and it looks like the y value would be 3 there. Alright, now we want to do the same thing but from the right. So we follow the path from the right, get to 2, and my y value is 1. So we can conclude that the limit as x approaches 2 of f of x does not exist, D and E, because the left and right hand limits are not equal. Okay, so that's really important to remember. F of 2 is where it's filled in here. I'm circling it, and it looks like f of 2 is 3. That's just the function value at 2. The limit as x approaches 4 of this function, well now, let me see if I can erase. I did it this time. Sometimes it doesn't erase for me. And I get bored of my colors, so I gotta change things up here. Something a little darker. Alright. Let's see how that works. Some nice green here. Alright, now we're looking at 4. So we go from the left and from the right this time because it's not specifying which way. So we need to look at both ways. And it looks like if we approach from the left and the right, we're heading towards 4 on the y-axis. F of 4, however, does not exist. There's a hole there. So this is to show that the function value doesn't have to exist for the limit to exist, which I mentioned earlier. Use the graph below to find the following limits. So these are involving infinite limits. If I approach 0 from the right, so here I'm coming along to the right, what's happening is this graph just keeps going up and up and up, and we reach infinity. Same thing if I head towards 0 from the left, I'm heading towards negative infinity. So the limit as we approach 0 doesn't exist because one's going up to infinity and one's going down to negative infinity. They are not the same. However, if I erase that and I look at going the limit as we're going towards negative infinity, so x is approaching negative infinity right here, what is the y value I'm approaching? That would be 3. And if I head up, head to the right, because x is approaching infinity, again, my y value is approaching 3. Okay, I did that. Okay, so we want to graph these functions and find the limits, if they exist. So f equals x squared. Pen, okay, eraser. Alright, how do I undo that? I don't know how I got that pink mark on there. You guys are probably laughing at me. Alright, we're going to have to deal with the pink mark because I don't know how to get rid of it. Alright, we're just graphing x squared here, so x squared should be one that you can do without thinking too much. 0, 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4. So our good old basic parabola. Alright, there it is. So zoom back out, and we want to find the limit as x approaches negative 1. Well, if I follow my graph towards negative 1, my y value that associates with that. Alright, so here we go. We're approaching negative 1 from, oh, gotta get the pen back, and the wrong color, from the left and from the right, and we look over, and lo and behold, my y value is 1. So the answer to that question would, I keep hitting the wrong button there. Alright, zoom back out. This limit is equal to 1. And then we do the same thing if we head from 0 from the left and to the right. I think you can see that that limit would be 0. If not, bring those questions to class or office hours. Alright, the second one, we're graphing 1 over x minus 3 plus 2. So you have to know a little bit of transformations there from your 163 or pre-calculus class. So your basic graph of 1 over x here is like this. That's just a real rough sketch. So what's happening with this one is we're moving the asymptotes up 2 and over to the right by 3. So let me erase this and I'll show you the transition here. So we have an asymptote because of the -3. Remember with when it's inside, like this one is, because x has been replaced with x minus 3, that's a horizontal shift. And the minus indicates that we go to the right. If it were plus, we'd go to the left. So we have this asymptote here. And then the +2 means we shift everything up 2, so I have an asymptote at 2, x equals, or y equals 2 rather than at the x-axis. And then we just sketch in each of these graphs. Alright, there's our graph, and we want to know what the limit is as we approach infinity. So as x is approaching infinity on this graph, I'll draw little arrows, it looks like my y value is approaching 2. And then the other one is find the limit as x approaches 3 of g of x. Okay, so find your graph and find x approaching 3. Here's from the left. Here's from the right. They don't match up, so this one is a D and E. And that's it for 1.1. Shoot, I did it again. Oh.